We're going to cover the last section of the notebook, the Python notebook corresponding to chapter 7 of the textbook Mining Complex Network. So we're talking about hypergraph. And in this part, we're going to be looking at a hypergraph built from real data. So the original data can be found in this GitHub repository, and it's about the scenes in the Game of Thrones television series. So the nodes are characters or named characters in the series. The edges or the hyperedge are a group of characters appearing in the same scene, and then hyperedges have weight that correspond to the scene duration in seconds. And we did a little bit of pruning, so we kept hyperedges with at least two characters, and we discarded characters with very low degree, so below 5. So the data is saved with the following in the following three objects. So we have the edges, we have the names of the character, and we have the weight of the edges. So let's load the data and build the HyperNetX object. And this is adding the full name character of the characters and computing node strength. So remember, unlike degree, we refer to node strength as the sum of the weighted degree. So in this case, it would be the total duration, scene duration for each character. So we do a little bit of EDA, exploratory data analysis. So for example, what is the distribution of edge size? You have mostly small edges, so seen with involving just a few characters, but it can go up to 24. Those are the named characters, so not all the characters that are not mentioned, that are not named specifically in the series. And then distribution of the edge weight, that's the duration of the scenes. So most scenes have duration, under 400 or 500 seconds, so 10, 15 minutes. But some scenes are really, really, really long. That's almost like 50 minutes or something. Probably some epic battle or something. And degree distribution also. Again, most of the nodes have relatively small degree, but some are very high in the hundreds. The main characters, uh, most almost surely, we're going to see that soon. And then the distribution of a node strength. So the total scene appearance for the characters, again, it varies a lot. Most of the characters do not appear, that much. But of course, the main character will appear in a lot of scenes. So for total duration, that is pretty high. So we store all of those in a data frame, and if we sort the rows with respect to the strand, so the total duration, scene duration, we can see the main characters of the series have appeared the most, which of course makes sense. So we saw different notion of centrality and betweenness. So in this cell here, we're computing S centrality and S betweenness, S harmonic centrality and S betweenness for S equal 1 and S equal 2, and adding that to our data frame. You can see in this case the values are of course different for S equal 1 and 2, but they're not drastically different because there is some overlap between the edges. So the paths are not going to be so drastically different between S equal 1 and S equal 2. Okay, so we're going to be doing, we can also compare, before we do clustering, we're going to be comparing the centrality measure with the measure we get with the two-section graph. So we can build a two-section graph, we know how to do that, and then compute the betweenness and the harmonic centrality, and comparing those to the values we got for the S betweenness and S centrality. If we use the same normalization, because there are different definitions, those values can be normalized in different way, but using the same normalization, we get exactly the same value here for betweenness on the two section, and betweenness, S betweenness with S equal 1, and the same with harmonic centrality on the two section graph, and harmonic centrality with S equal 1, the same values, and we can see that if we compute correlation, so for example, for harmonic, when S equal 1, we have perfect correlation, and even when S equal 2, we have pretty high correlation, and the same for the betweenness. Okay, so we're going to be doing clustering and computing hypergraph modularity. We're going to be using tau equal to 3 in our definition of modularity. Remember, this is the exponent that we use when we compute the edge contribution part of the modularity. So first, let's visualize the two-section graph. So you can see that we should be able to build some strong communities here. There are some groups that are pretty clearly going to be in the same community. And for example, these nodes here, they form a well-separated clique or almost a clique that is actually a theater, a group, a theater troupe in the series. Okay, so if we were to do random clustering, just to give us an idea, then those are kind of the value for the hypergraph modularity we would get. So around 0, maybe between, up to 0.03, 0.04 maybe. So if we want to have a good clustering, we should be able to get hypergraph modularity significantly higher than, values such as 0.03, 0.04. So that's what we're going to see. And here's one trick, because I mentioned a few times already that one difficulty with hypergraph algorithm is that they're often much slower than running a similar algorithm on a graph. So one kind of in-between solution one can use is to actually run something on a graph, but then use a hypergraph-based measure. And here's an example where we're going to actually lead an algorithm 100 times on the two-section graph built from our hypergraph. But we're going to compute for each time we run the clustering, we're going to compute the modularity based on the hypergraph based function. So sorry, we're going to compute the hypergraph modularity function with this tau equal to 3. And then we're going to keep the partition, the clustering that give us the best hypergraph modularity. So this is an example of using something that is fast on a graph, but using a measure that really takes into account the fact that you have a hypergraph. Okay, so let's run this. And that's not going to take too long, despite the fact that we're running the algorithm 100 times. And so it took about like less than 10 seconds. We get a value that is significantly above 0 for the hypergraph modularity. And if we plot the two-section graph with colors for the clusters, you can see that it seems to make sense, at least visually. Okay, we're going to be looking at composition of one of those clusters a bit later. And another thing we can do is to look at the edge composition. So do we have mostly community edges? So is the clustering really separating the vertices so that the edges remain, pure or are pure, almost pure? And it seems to be the case that this is with our best lead-in cluster on the two-section graph. And you can see the largest number of edges are edges of size 2, where both vertices are in the same community. Then edge of size 3, where the three vertices are in the same community. 4, 4. 2, 1 is not a community edge because it's an edge of size 2, where you have one vertex in two different, and each vertex is in a different community. But then you have 3, 2, that's a majority. 5, 5, there's 6, 6, there's 7, 7, 5, 4, 4, 3. So you can see that there seems to be a lot of, good community edges with this partition of the vertices. We can also apply a hypergraph-based clustering algorithm, which is Kumar's algorithm. And while this runs, sorry. So, and we get actually slightly worse in this case for the hypergraph modularity, and this is value for the AMI. This takes about 2-3 minutes to running H. Louvain on this hypergraph, but you should be, if you uncomment and run, it takes 2-3 minutes, you should be getting slightly higher value for the hypergraph modularity and for the AMI. Okay. And as I mentioned earlier, we can look at the composition of the clusters. So, for example, if we pick one of the main characters, Daenerys Targaryen, we can look at the other vertices that are in the same cluster And in this case, they're in the same cluster with respect both to the Leiden algorithm and to Kumar's algorithm. And those are, characters that do interact a lot with this main character. So it's not too surprising if you're familiar with this theory. We can also compute simplicial ratio. In this case, remember we had examples before with, HABCD and what have you, where simplicial ratio was, just slightly above 1. But here, we have a value that is clearly above 1. Simplicial ratio of 3.6 means that we are, 3.6 times, more surprised than we should than with respect to the number of inclusion of vertices than we would be if we were to draw edges at random. So not surprising again, because there's a lot of scenes that involve a certain number of characters, and then there are other scenes that involve a subset of those characters or a superset of those characters, and this is to be expected, of course. We can also compute the individual simpliciality by looking at the ego net for each of the vertices. And if we do that and we rank the characters with respect to their individual or ego net simpliciality, then you see that, there are some values with, pretty high simpliciality, some characters, sorry, and there are some characters at the bottom of our data frame that have, pretty, actually less than 1 in terms of the simpliciality. So we're going to look at a high simpliciality and a low simpliciality example. So with high simpliciality, and this is just drawing. So the node itself is here, and then we're just drawing all the edges involving that particular vertex, this particular node. And you can see there's a lot of overlap happening here between the edges, thus the high simpliciality. Another way, if you use XGI, you can use the convex hull view. You might prefer that. Again, you can see there's lots of overlap. But if we look at the character with low simpliciality, then you can see that maybe it's not so clear in this drawing, but there's not as much overlap in this case. Actually, there's not much overlap. It looks a bit more like a star, and this is probably more clear if we look at the convex hull type view. You can see that, there's much less overlap between the composition of the edges or the hyperedges. In XGI, you can also look at a three-dimensional view where you look at edges of different size on different planes. And you can see those are the edges of size 2. Here you have edges of size 3, and they don't touch the same vertices. And here you have edges of size 4. Okay. Degree size correlation is also something that we address in the textbook, and we have a function to that to compute that. In this case, the correlation is, positive, but just marginally positive. So there doesn't seem to be much difference in terms of the degree distribution, depending on the edge size. Maybe it's slightly higher here, but this one is lower. So, it's a bit difficult to have a strong conclusion. Even if we group the edges into 3 different ranges for the size, so edges 2 to 8, 9 to 16, and 17 to 24, the degree distribution, increases, but very, very slightly. So there's positive correlation, but very, very small. Another thing we discuss in the book is this Rich Club coefficient. And so let's do the computation here. Here we go. So for the Rich Club, in this case, there's no closed form formula we can use. So what we can do is we first compute these values phi of k, the nodes that have degree larger or equal to k. And then to generate the denominator, we need to go via sampling. So we're generating random bipartite graph and computing this way the denominator to obtain our Rich Club plot, which, is not much above 1 here. So remember, in the case where we really had a Rich Club phenomenon, there was a huge bump, well above 1, but we don't seem to have any of that effect with, or nothing strong really, with respect to this data set. And also in the book, we discussed the notion of coreness, more specifically this definition of KT hypercore. So remember, the KT hypercore is the maximum subgraph where the node has degree k or more, and each edge contains at least a proportion t of its original nodes. Okay. So that is something that is not really, that is really an extension of what you can do with graph, where all the edges are of size 2. Now you can include edges that are that don't contain necessarily all the vertices, so long as they contain at least proportion t of the original vertices. And so here's a function that can allow you to compute hypercoreness for hypergraph for values k and t. And you can uncomment this to compute a larger number of values because it takes a couple of seconds. But here I'm just going to compute it for t equals 0.9 and plot the result. So we have t equals 0.9, and then we're for a different value of k, you have the size of the kt hypercore. So if we look, for example, k is 18, which is about here. Okay, so and t equals 0.9. We're going to be, so we're going to recompute this hypercore and the vertices that are part of this hypercore, and then we're going to be building a visualization of this data set, a graph and a visualization of this data set that is part of this hypercore. And you can see this; those are mostly, main characters that are very, very heavily connected between themselves. And again, we can use the XGI view, which is a different way of looking at things. Again, which one is clearer? It's up to you. But this is an example of a highly connected sub-hypergraph, if you want, obtained with this KT hypercore decomposition. Okay, the last thing I'm going to mention is those are different data sets, so-called contact hypergraph, and the reason for this cell here below is that there's a couple of questions at the end of chapter 7 that refer to those data sets. So a contact hypergraph is built when when you have individuals, usually it's people, and when they come in close proximity, like physical proximity, then if two or more people are in close proximity for a certain amount of time, then you build a hyperedge. And one of those data set involve primary school. So you have teachers and children, and there's about 12,700 edges of size 2 to 5, and there's 242 individual. There's also like ground truth communities, if you want, that correspond to the 10 different classrooms and the teachers. And so the data is included, the edges are included in this text file, and then the labels, the node label 1 to 11 that correspond to the 10 classes and the teachers are included in this other text file. And then the same thing for a high school data set. And this is an example. This is the high school data set. This is how you would load it, build the hypergraph, build a two-section graph. In this case, read the ground truth community, and here I'm coloring the nodes with respect to the ground truth communities. And I think that's it. The other cells are just to build some of the drawings in the textbook, and that's it.